me recording this meeting, you can always leave the room. You are not obligated to stay against your will. So you can leave anytime you want. Okay. So with that, I would like to start today's technical session. So I'm going to discuss about the effect of scan rates, concentration, and role of supporting electrolyte on the shape and structure of transient polarization curves like CV and LSV, and how we are going to use that for some specific applications. So this will be done for first 3 minutes, first 15 minutes. Then we can have 45 minutes for the discussion, and I will be answering all your queries and questions. And you can also suggest me if you find anything wrong with my answers or clarification or the presentation I'm going to make now. So with that, I would like to begin now. Yes, let me share my screen first. Yes, I hope you all can see my screen now. Yeah. So I remember in the last week's technical session, I introduced about the fundamentals of LSV and CV, and I also introduced you all about how we are observing the duct-shaped voltammogram with the diffusion limited reaction, electrochemical reaction with cyclic voltammetry, and the role of diffusion layer formation in this slide, right? So I assume that you probably remember the things I said in my last week technical session. If you still have doubt, you can always ask me at the end of the presentation. I will be happy to explain it again to anyone or every one of you. Yes, and the next thing is that now we know the fundamentals of CV and LSV, and there are certain things that can affect the structure, shape, and a lot of other important characteristics of this voltammograms, cyclic voltammograms and linear sweep voltammograms. The very first thing is the scan rate, particularly when your reaction is limited by the diffusion of the electroactive species. Okay, so the diffusion of electroactive species is an important thing, particularly when your reaction is limited by the diffusion, because once you insert an electrode into an electrolyte solution, there is a double layer formation instantaneously, which we know. And because of the double layer formation, there exists a potential difference across the electrode-electrolyte interface. That potential difference is nothing but the open circuit potential of the half cell in which we are monitoring the reaction of our interest. Okay. But now what we are going to do is that we are going to connect a third half cell, which is literally the reference electrode. And with reference to the potential of that reference electrode, we are going to control the potential applied on the working electrode. Okay, so this is what we are doing in 3 electrode system. So in linear sweep and cyclic voltammetry techniques, what we do is that we are not only applying some potential, we are actually sweeping the potential from one potential to another potential, from point 1 to point 2 in the potential scale. Okay, so if you stop only at the vertex potential, that is called LSV. And if you come back to the starting potential, that is called cyclic voltammetry. Okay. So in all these cases, the rate at which you are sweeping the potential, which is basically known as the scan rate or the sweep rate, will be having huge influence on the current density, particularly on the maximum current you observe and the peak potential. Okay, for diffusion controlled reaction. So here is a graphical example animation shown here. This particular image shows how the rate of the sweeping or ramping is increased with the time. So when you sweep the potential from V1 to V2 at a very slower scan rate, you take more time. Okay, in the time scale we take more time, but with the increasing scan rate, the time is reduced. So we literally give the interface less time to build up a thicker diffusion layer. In my earlier session, I told that thicker the diffusion layer, lower will be the amount of electroactive species reaching the electrode surface, so that the current will always be lower. So now you know, when we perform the reaction with a very low scan rate, there is huge time for the diffusion layer to grow thicker and thicker, so that it forbids the flux of the electroactive species diffusing from the bulk of the solution to the electrode surface. So what happens then is that the amount of electroactive species reaching the surface is reduced, significantly reduced. So the amount of oxidation, the quantity of oxidation or reduction happening is also reduced. That is why you see lower current density with lower lower scan rate. So when you increase the scan rate, suppose for example, for such a high scan rate, you are literally giving very low, very less time for the interface to grow a thicker diffusion layer. As a result, the flux of the electroactive species is very high with a higher scan rate. Okay, so the amount of electroactive species in the electrode surface is higher, so that the current of oxidation and reduction is also higher. So that is why with the diffusion limited process, with the increasing current scan rate, we see increasing current density, peak current density. So this is what the very fundamental thing you should know, and you should also understand why is such a relationship is observed with scan rate. So scan rate is actually directly proportional to the peak current. So with this lower scan rate, you observe lower current density. With higher scan rate, you observe higher current density. It is because scan rate and diffusion layer thickness are inversely related. Because with the lower scan rate, you have thicker diffusion layer. With the higher scan rate, you have thinner diffusion layer. So this is what you should understand from this particular slide. So this is basically controlled by the Fick's law of diffusion. So those who have studied BTech chemical engineering and chemical electrochemical engineering from SICRI, you all have this fluid dynamics where you cannot skip this famous law of diffusion by Fick's, right? By Fick. So this states the flux density and how it is related to the change in concentration at the interface with the thickness of the diffusion layer. Dx is nothing but the thickness of the diffusion layer. Okay, this is the change in concentration. So at any given point of the diffusion layer, the concentration can be related with the flux of the electroactive species reaching the electrode surface using Fick's law. So this is directly answering our question why with the increasing scan rate we see increasing current density. Okay, now we should see the effect of other things like an ion can interact with an electrode surface in various ways. Like there is not a single way, only in which or only by which it can be reduced or oxidized. There are many ways in which the electron can be transferred between the electrode surface and the electroactive species in the electrolyte solution, mainly the diffusion layer. Okay, so when the electroactive species diffuse through the guy layer, Helmholtz-Perrin layer, and inner Helmholtz plane, either it can directly get attached to the electrode surface, absorbed electrostatically to the electrode surface, or it can stay away, separated by a layer of a monolayer of water molecule or a solvent molecule between the adsorbed ion and the electrode surface. Okay, so there are two kinds of adsorption. The first one, in which the electroactive species directly attached to the surface, attached to the surface of the electrode, is called specific adsorption. Okay, the second part where there exists an solvent monolayer. Okay, the Bogris model of double layer. So if the electroactive species cannot penetrate through this solvent layer on the electrode surface, that kind of adsorption is known as non-specific adsorption, and electroactive species that are interacting in this manner with the electrode surface are called freely diffusing ions. Okay, so this is freely diffusing ion in which the electroactive species cannot penetrate the solvent layer on the electrode surface. Okay, so in such case, so increasing scan rate, how does the increasing scan rate affect the shape and structure of a cyclic voltammogram? In cyclic voltammogram, we usually see three things. One is the peak-to-peak separation from cathodic to anodic. Okay, so how does the peak-to-peak separation varies with the increasing scan rate? How does the ratio between the anodic peak current and cathodic peak current varies with the increasing scan rate? Okay, and second thing, if we can choose either anodic peak current or cathodic peak current and check how does it vary with the scan rate, or how does it related with the scan rate. So in the case of freely diffusing ion, which is the relationship between the peak current and the scan rate is given by the famous Randall-Sevcik equation, which states that the current will linearly increase with the square root of the scan rate. Okay, so this is very, very important. So with the square root of, if the current varies linearly with the square root of the scan rate, you will you can blindly say that your electroactive species is not penetrating through the solvent layer on the electrode surface, but it is transferring charges, I mean electrons, through outer sphere mechanism proposed by the absolute rate theory of Marcus, for which he won a Nobel Prize. Okay, so this is how the freely diffusing, non-specifically absorbing ions involved in electron transfer. The main thing is that the current will linearly vary with the square root of the scan rate. So what happens when an electroactive species absorbs specifically? I mean, when the electroactive species penetrates through the solvent layer and attaches to the surface before it transfers electron across the interface between the electrode surface and the species. So this is given by the modified equation of modified Rendell-Sevcik equation, but it is not called Rendell-Sevcik equation. All the other conditions are the same. The peak-to-peak separation will be closer to 59 millivolt, and peak position is independent of scan rate, which will not shift anodically or cathodically with increasing scan rate, and the current ratio, IP-IEC ratio, will also stay the same, but the current will linearly increase with the scan rate instead of the square root of the scan rate, what we have seen for freely diffusing ion. So this is very, very helpful for people, those who are working in the area of sensors. People use electrochemical sensors for detecting various anions, cations, and the various analytes in the solution. But the main question that they need to answer is that how does their analyte or molecule that they are sensing is interacting with their electrode? Is it interacting directly with the electrode? Does it penetrate through the solvent layer on the surface, or it is acting by the Marcus theory? I mean, transferring the electron by outer sphere mechanism, by throwing the electron up and catching it from away. So this you can do it simply by varying the scan rate and observing this parameter, which is nothing but plotting the current density against the square root of scan rate and scan rate. So whichever is the linear, whichever is resulting in the linear relationship, you can easily identify how your analyte is interacting with your electrode surface. So this is how you can use the scan rate effect to find out the nature of interaction of your analyte with the electrode surface. So I think 15 minutes is over. So I'll stop here. Let's continue next week about the applications and how we can calculate diffusion coefficient and what are the other applications and what happens when there is huge solution resistance, what are the roles of supporting electrolyte. These things we will see next week. And if you have any specific doubt in these two slides, you can ask me now. And apart from this, if you have something else, I will also be happy to be answering you. Okay, so with that, yeah, let me come back to the meeting room. Yeah, with that, I would be happy to be answering your question. So those whoever have questions, you can raise your hand and I can make you a host so that you can ask your question. So yeah, Mr. Anmandal, you have raised your hand. If you have a question, please go.
Yeah, hello, sir.
Yeah.
Yeah, so my question is, in case of this electrocatalysis, we do this preconditional at very high scan rate. And after that, when we take CV or LSB, we generally use low scan rate, like 5 or 10 millivolt per second. Okay, so you said that whenever this scan rate is low, then this diffusion layer will be very thick and it is very difficult for the electroactive species to come in contact with the electrode.
Yes.
So will it be better now to measure the CV at higher scan rate so that the electroactive species will come in contact with the electrode? So we'll know the activity of the catalyst.
Yes, that's an excellent question, Mr. Mondal. So I'll answer you. I need one more thing. I want to know whether your electrocatalytic reaction, what you are referring now, is diffusion limited or not.
Like I generally do oxygen evolution reaction.
Okay, which is not limited by diffusion. Okay. at extreme pH conditions like alkaline and acidic condition. Oxygen evolution reaction is not limited by diffusion. Okay.
Okay.
Okay. In that case, increasing scan rate or decreasing scan rate will not affect your kinetic current because it is not limited by diffusion. So there is no role of scan rate. But there could be small difference, negligible difference with the increasing scan rate. There could be a slight increase in current density. That is because with the increasing scan rate, you are adding up the capacitance current contribution to the overall catalytic current. And there is also a catalyst oxidation current. So with the higher scan rate, the oxidation of catalyst becomes higher.
Yeah.
Okay. So that current will also get added up to your OER current. So uh, literally, with the increasing scan rate, the kinetic current of OER, which is not limited by diffusion, will not vary with the scan rate. Okay. So there is
Okay.
no role of diffusion layer here, because in the case of diffusion limited process, what happens is that the products which is forming as a result of oxidation or reduction stays in the interface, right? In the diffusion layer. Yeah, the concentration of the product increases. That also contributes to the growth of the diffusion layer. But in the case of oxygen evolution reaction, it is a gaseous product. So it evolves out, it escapes out of the solution.
Yeah.
Okay. And moreover, in oxygen evolution reaction, the electroactive species is water. And precisely in alkaline condition, it is hydroxide. We always perform this reaction with 1 molar KOH or zero point 0.1 molar KOH, at which the concentration is sufficiently higher enough in order to prevent any diffusion limitation. Okay, the concentration is too high that the diffusion layer that can be formed because of the depletion of hydroxide anion in the interface can be nullified because of its high concentration. So
Okay.
there is purely kinetic control, how fast your electrode is catalyzing this OER reaction. Moreover, your gaseous product is also escaping out of the solution. So
Yes.
literally there is no diffusion layer. Okay. So there is no
Okay.
diffusion layer. When there is no diffusion layer, you don't have to worry about the scan rate. But there are other factors, like I said earlier, the double layer capacitance and the catalyst oxidation current. These two can add their current contribution to the catalytic current, and you may see some very slight increase. Maybe if you are working with the catalyst which is delivering about 200 or 300 milliampere per centimeter square at a very high potential, you can see some 5 to 10 milliampere difference with increasing scan rate. Not much.
Okay.
So even then, if your purpose is to use this LSV or CV for TEFL analysis, I would always say that you record it with a very low scan rate possible, because the capacitance current will always shift your exchange current density value like unimaginably. You wouldn't believe the order of magnitude of difference between the exchange current density value that we would determine from the TEFL plots of the same catalyst, but recorded at the two different standard, like 5 millivolt and 100 millivolt. You will see at least 2-3 orders of magnitudes different in the exchange current density value because of this current capacitance current contribution. Okay.
Okay.
So if your aim is also to use this LSV or CV for TEFL analysis, so you please choose some very low scan rate, like 1 millivolt or 0.1 millivolt, something like that per second.
Okay.
Yeah.
Okay. Thank you, sir.
Yeah. Yeah. If any of you have any question, you can ask. Yes, Dr. Dhanasekhar. Mr. Mundal, can you make Dr. Dhanasekhar as a co-host?
Sir, I can't see any option.
Oh, okay. So you are a host, right? Can't you make him a host?
Yeah, because I am not seeing any option to make him host.
Okay. In the participant list, there is 3 dots on his name, right side to his name, and there should be.
Yeah. Okay. Okay.
Yeah.
Okay.
Please do. Whenever someone asks,
Yeah. Yeah. Definitely.
raise, please do that. Thank you. You're being a great help to me now. Yes. Dr. Dhanasekaran, you are a host now. You can ask your question by unmuting yourself.
Yeah, thank you. Thank you for the opportunity.
Yeah.
I have a couple of questions. First
Yes,
question
please.
is, as per some of the months back, we discussed means how to do backward reactions. for why what's the purpose means when I'm running the CV or LSV, that catalytic peak, that means nickel hydroxide to oxyhydroxide peak existing broadly. In that doing the backward reaction, I try to do that backward reaction. It is not I cannot collect the correct data. So can you explain how to do that?
So do you have the data with you now?
Now actually I have it, but not in that system. It is in C.
Okay. So if you show me, it would be better for me to.
Okay, in coming days I will for the
Please.
next session I will share it.
Yeah, it is because wait a second, I might have a data to show you. Just a moment. Yes, Shubhas, just a moment. Let me answer the question from Dr. Dhanasekaran, and I'll come back to you. Just a moment. I'm taking one of my data to show you how can we do that. Just a moment. Yeah, Dr. Dhanasekaran, can you see my screen?
Yes.
Yes. Yeah. So this is an example. As you can see here, this is a set of NIFE based electrocatalysts and studied for OER. As you can see here, the oxidation current is over 15 milliampere. So I cannot measure the potential over potential here. Okay. So so the only thing I can do is that to take the backward sweep in which there is no just a moment. So can you see the backward sweep here? The same plot, but different. Yeah. So in this case, at 10 milliampere, so there is no issue of redox peak. So here you can easily measure the over potential and report it.
Yes, but how can I do that? From negative, can I fix that potential?
No. You don't have to acquire the backward sweep. So you can just delete the forward sweep here and only plot the backward sweep.
Okay, but doing that normal CV only, forward and backward.
Yeah. So you can record a CV normally and just delete the forward scan and only show the backward scan. So that is sufficient.
Okay, but I am doing that. Okay,
from that, if you try recording a backward sweep from 1 to 0, for example, you will not see such a structure because there will be some oxidation when you come back.
Yes, I am trying to from your image 1.7 to 0.8.
Yeah. So you cannot achieve such a structure when you do it backwards.
But here also, see in forward reaction and to the backward reaction, some potential difference is there.
Yeah, that is because this one is not IR corrected. This one is IR corrected.
Oh, after supposed to okay.
Yeah. That's why you see the difference. Okay, that's because of the IR compensation.
Okay.
Yeah.
My another doubt. My question is. Normally we are doing in a CV, LSV for OER, other HER at 10 milliampere. Some lower potential we get. For example, at 10 milliampere for OER reaction, 260 to 70 millivolt I got. But in that chronoamperometry or chronopotentiometry, I am applying for fixed potential, fixed current. That is the correct. For chronoamperometry, I am applying for 250 millivolt. It is not giving that correct current density. Okay. Particularly for chronopotentiometry. So can you explain that?
Yes. So from your question, I understand that you did not read my recent paper on worrisome exaggeration of activity of electrocatalyst destined for steady state water electrolysis, published recently in Journal of the Electrochemical Society, in which I have chosen only this problem, whatever you said now. Okay, the difference you observe in activity between LSV and CV with CA and CP. Okay, so with the steady state technique, what happens is that in all transient techniques, we do not let the interface to achieve a steady state. Okay, so what we measure is that a fleeting response. Okay, that's why it is called transient response. We are not letting the interface to be at the same potential for a sufficiently longer time in order to see a stabilized activity. Okay,
Yes.
so that is the reason why you see always a higher current density, a little bit higher current density with LSV or CV. But when you perform chronoamperometry or chronopotentiometry for the same potential or the same current density, your activity will always be a little lesser than what you observe in LSV or CV. This difference increases with increasing over potential. This is what I recently found. And I also addressed the reason for that. It is because two things. One is that with the scan rate and because of the transient nature, the response what we observe is transient in nature, so that it is not a steady state response. So we know all electrochemical interface. When we measure the current at the very first point, it will always be higher. So even if you perform chronoamperometry, you will see this. When you set a potential and start chronoamperometry experiment, you will see the current is declining from a very high current density. Then it will slowly attain the steady state.
Constant.
Right?
Yes.
But the same is true for CV also. If your scan rate is very, very high, so when you change the potential from one potential to another potential, okay, and you are not letting the interface to stay at that same potential in order to let it to reach a steady state. So you are measuring actually the transient response in which it always gives higher current density. So do not believe the activity whatever you are measuring using LSV or CV. Whatever you are measuring with chronoamperometry or chronopotentiometry is what the exact activity. Okay, but we cannot perform chronoamperometry or chronopotentiometry for a very long time at all potential of the potential window in which we are studying, right? So to address this issue, we proposed a modified technique called sample current voltammetry in the recent paper of mine, which I told you. I'll share the link so that you can.
I have that paper. Yeah, electrochemical system.
Yes. In that paper, you can see how you can construct a polarization curve, sample current voltammetry, which is quasi steady state in nature, but it does not represent the transient current. Also, it does not take up longer time like C or CP used to take up. So the advantages of my method is that you can avoid huge time consuming CACP. At the same time, you can also ensure higher accuracy in the activity you measure. Okay, so that is why you see this difference.
Okay, and one more related to my these questions. For LSV and CV, we can current density we can add by the current divided by the surface area. For that issue, we can used in that chronopotentiometry. We can use or not use.
Yes, you can use if your electrode surface area is 1 centimeter square.
Okay. For example, I am using nickel foam 0.25 into 0.5 centimeter square.
Yes.
Both side, can I add it or one side is enough?
With 3D nickel foam, both side is considered to be a single side.
Oh, okay.
Yeah, generally it is considered to be a single side. Yeah.
For example, a FTO plate, one side only active surface.
Yes.
There is only one side.
That is true. Yeah, that is true.
Okay.
But with the foil type of electrodes in which the material can be coated on both sides and the activity can be observed on both sides, it is still considered as just 1 centimeter square area.
Yeah. This is my biggest doubt. Yeah. Okay, thank you. Thanks for the clearance.
Yeah, thank you, Dr. Dhansekhar. You can mute yourself. And Mr. Mondal, could you please make Subhash as a co-host? Subhash Kandasamy?
Yeah, I'm a co-host now. Can you hear me now?
Yes.
Yeah. According to what you said, if the electroactive species is diffusion limited, then if we increase the scan rate, then the current density should increase, right? So I'm working on a chlorine evolution reaction both for seawater and for industrial purposes. So it is a diffusion limited reaction because it is mixed with water, and every time the chlorine species has to reach the electrode surface, So, but if in it is diffusion limiting. So when I'm doing at let's say like 5 millivolt per second LSV, let's say I'm getting 100 milliampere at my peak potential, and then when I'm increasing the scan rate to 10, the current density is increasing according to what you said. But when I increase it to 20 or 30, I'm experiencing a less current density value.
Okay.
So can you help me with that?
That is a peculiar case. So I have not worked in this area, but what I guess is that there are a lot of possibility with the chlorine evolution reaction, because when you oxidized chloride, you cannot be sure that only a product forming at the interface is dichloride. I mean dichlorine molecule, right? Dichlorine gaseous molecule. There is also hypochlorite, and there is also chlorous oxide, and also perchlorate. All these can form. So among them all, the only gaseous product is chlorine gas, right?
Yes.
That too will dissolve in water fairly, resulting in hydrogen chloride.
Yes.
Okay.
Yes.
So since you have these many probability and possibilities, I guess with the higher scan rate, when the flux is very, very high, you might be forming a non-gaseous product at your interfaces, which is helping your diffusion layer to grow thicker, irrespective of your higher scan rate. That is why you may see decrease or lowering in current density. But in order to validate this hypothesis, you might need in situ Raman spectroscopy, or you might need DEMS, differential electrochemical.
We have DEMS, but we have a problem.
Then
We
it
are
is fine. You should be
trying to
able
define a cell for that.
Oh, okay. Yeah. So with the DEMS, you can easily find it out. You can easily follow what is happening with the higher scan rate. So if you observe some other product in higher quantity, I mean, if the selectivity of the electrode is shifted because of the increasing scan rate and increasing, it is not only the selectivity is not only depending on the electrocatalytic activity and the intrinsic nature of the electrocatalyst what you are using. It is also depending on other factors, particularly when your reaction is diffusion limitation. I mean, limited by diffusion. Okay. Yeah. So you must examine using DEMS what is happening at a higher scan rate, and if there is a formation of a different product which is not escaping from the solution, like chlorine does, you may assume that because of this non-escaping product, there is a thicker diffusion layer, and because of which you are witnessing a lower current density with a higher scan rate. Second thing is that there is one more thing. There is another thing, which is the kinetics of oxidation of I mean the rate of oxidation of chlorine. This is also very important, because sometimes the rate of the reaction may be very slow, I mean slower than that of the scan rate. Okay, in that case you might have swept the potential already beyond the oxidation potential, but because the rate kinetics of the reaction is very, very slow, you might be seeing very low current density. So these are the two reasons. One of these two reasons should be valid for your observation. Either your kinetics should be very, very less when compared to the higher scan rate what you are using, or your interface is shifting the selectivity and resulting in a non-escaping and non-gaseous product, which is causing your diffusion layer to grow thicker.
So these non-gaseous products might also affect the over potential during chrono.
Yes, of course.
Okay.
Yes. So was it useful?
Yeah. It's really useful.
Thank you so much. Yeah, I'm glad that you could join us today.
Yeah, thank you.
Yes, Mr. Abhishek Rai. Mr. Mundar, please make Mr. Abhishek Rai as a host.
Yes, sir.
Yeah, please go.
Sir, actually, I am reading your recent paper, The Significance of Properly Reporting Turnover Frequency.
Yes.
Yeah. So actually, here that I found that for HUPD and the co-stripping method are actually CO stripping method are used. But for HEF catalysts like molybdenum and tungsten, where no such redox peaks are observed in HEF, how I can calculate the TOF?
Yes. And I remember I have also I have also mentioned the way for that, but that is not an accurate way. But for catalyst for which hydrogen under potential deposition or CO striping or copper under potential deposition, lead under any type of under potential deposition, or the redox peak charge integration cannot be used, you should always assume that all the electrocatalytic sites that you have loaded onto your substrate electrode are active, and you should calculate all the in every single atom of molybdenum and tungsten in your loaded catalyst, and assume that all of them are involving in the electrocatalytic reaction, and calculate the TOF accordingly. So this is the only way now. But there are some advanced way for which you will need electrochemical AFM or electrochemical AFM and electrochemical AFM, and also you can use STM, electrochemical STM.
Okay.
Scanning done STM, yes, STM.
Okay.
Yeah, in which you can physically count each and every active site just by letting your probe touch the surface while you perform the reaction, so that you can literally count every active site on your surface, and you can determine the number of active sites available. And what people usually do is that this method is very useful for a monolayer catalyst or a single crystal catalyst, because we know that in a monolayer catalyst, a similar pattern is going to be repeating after some time. Similarly, for a single crystal catalyst, if you have a highly faceted face, like some Miller index, like 00N face is predominant, you can assume that after measuring the, after counting the number of active sites for a limited area, you can always extrapolate it for the overall area, so that you can easily find out the number of electroactive sites available. But these are all requiring some highly sophisticated instruments, which to which we are all not given a chance to connect it with. So it is always better to go with the 100% assumption method. So did you see? Yeah. Did you see the flow chart I have given in the paper at the end?
Yeah. That's yeah.
There it is mentioned.
Another question that TOEFL analysis that I'm found that you are saying that a TOEFL sub should be 100% IR corrected data.
Yes.
But why that from 100% IR correction? Because sometimes some papers are done from 75 or 85%
yes, that is not correct, Dr. Roy, because we all know that TOEFL analysis results from Butler-Wimmer theory, right? BV theory. In Butler-Wimmer theory, the Butler-Wimmer theory is nothing but it is simply the current potential relationship, in which the potential is assumed. It is derived based on some assumption, and one of such assumption, very important assumption, is that the potential, what they said in that equation, is free from IR drop. But in real case, no potential can be free from IR drop.
Yeah.
Okay, so since TOEFL equation is derived from BV equation, and in which the over potential term is said to be IR free, we must also use the over potential what we use for TOEFL plot construction to be 100% free from IR drop. So that is why.
Okay.
Yeah.
And the last term is that from just before you said that from the Randall-Lipschitz equation, that current is proportional to the square root of scan rate. That I'm just missing that. When it's proportional to the square root of scan rate, then what happened?
That means that your electroactive species, which is undergoing the reduction or oxidation reaction, is not specifically adsorbed onto the electrode surface. It is always separated by a layer of solvent molecule on the electrode surface. So the electron transfer happening between the electrode surface and the electroactive species are occurring via the outer sphere mechanism, the very famous mechanism proposed by Professor Marcus, and the theory is also named after him, Marcus theory. Or you can also you may also know it in the name of absolute rate theory of electron transfer, for which he won a Nobel Prize.
Okay.
Yeah.
Thank you.
Yeah. If you want to know more, you can simply type Marcus theory Wikipedia. There are enough information. Yeah, there is enough. Yeah, there is enough information.
Thank you.
Yeah, Mr. Parag Chavan, please go if you are a host. Mr. Mandal, can you make him a host?
Yeah, I've already made him.
Yeah, Mr. Parag Chavan. Mr. Chavan, are you there? Okay. I think, yeah. He's unmuting, but we cannot hear you. You're unmuting yourself, but we cannot hear you still. Why don't you text your question to the chat box? Yeah, you have already did. So I'm sorry. So which electrode should be chosen? GCR, PT, or AU for HER and OER? So I assume that you wanted to know which substrate electrode is to be chosen, right? So it doesn't matter. So if you have access to PT electrode or a AU electrode or a GC electrode for OER, you can always choose any one of them. But I would advise you to go with GC, because carbon does not have much activity towards OER like gold or platinum does at higher over potential. And the second thing is that if all these metals can be oxidized, all these elements, I mean carbon, platinum, and gold, can be oxidized at a high anodic potential, resulting in their oxide compound. So PT will be oxidized into PTO and PTO2. Similarly, AU also can be oxidized into AU2O3, I think. Yes, gold oxide will form. But in highly acidic condition and highly alkaline condition, these oxides can be dissociated and dissolved as metallic cations, and those metallic cations can migrate always towards the counter electrode, deposit over the counter electrode, and may create some problem, particularly when you are performing your study for HER reaction. Okay, so when you do HER, never use platinum or gold as a counter electrode. Always go for a graphite electrode or a carbon cloth, carbon fiber paper, anything that is made of carbon. Okay, so never use platinum or gold. And if you are performing HER reaction with PT as a substrate electrode, never do that, because PT is the best catalyst for HER. You can never choose PT as a substrate electrode for HER studies. Okay, AU can be chosen because the activity of AU is not so good for HER, and it also has quite high over potential towards HER. But you should be very careful about limiting your potential window, HER potential window, when you choose AU as the substrate electrode. But with carbon, again, you don't have any issue. You can enlarge the potential window from 0 volt to -1 volt against RHC with carbon as a substrate electrode. This carbon electrode can again be in any form: GC, carbon fiber paper, carbon cloth, or carbon nanotube coated felt, or simply graphite rod. So it doesn't matter. As long as you have carbon as the substrate electrode, you don't have to worry about either you are performing or performing HER or OER. But when you want to use other metals, you should always pay attention to what you are going to study with the substrate electrode you have chosen. Okay, I believe I have answered your question. Then the Somnath Dawal, yeah, last lecture you told me that demo for calculation of surface concentration using LSV. Ah, yes. Thank you for reminding me. So let me share you a screen here. Yeah. Just a moment. Yeah. Yeah, you see my screen, right? So yeah, so it is very easy to calculate in CV LSV. Just a moment, I'll choose a different brush. Yes, in CV or LSV we have something like this, right? So this is the potential scale, and this is the current. Okay, and our LSV curve is something like this. Okay, so this is the forward scan. But just a moment, sorry, I'm such a poor artist when it comes to drawing, so I'll just draw it again. Okay, yeah, this is much better. So we have a forward scan which is overlapped with the OER current, but when you come back there will be a clear reduction peak, something like this, right? So when you have two options, I would always advise you to choose this one. Okay, this one is better because this is also good, but since it is overlapped with the OER current, you will not know where to choose the limit for integration. So in with the backward with this, you will not have such difficulty. So you can just choose this area for integration. And since potential is always given in voltage and the current is in either ampere or milliampere, when you integrate this data, you will get some value, xxx value in milliampere into volt. Okay, so now we know the scan rate of the CV, what we are using for the calculation of electroactive size. So what we are going to do is that we are going to normalize this value, integrated area value, with the scan rate. So we know some XX scan rate. We know scan rate is expressed in millivolt per second. Okay, so what we have is that here millivolt, here you have volt. So what you can obviously do is that you can convert that volt also into millivolt, and you will have millivolt per second. So millivolt get cancelled, and you will have some number xxx number with the unit of milliampere second. Okay, if you convert this value into ampere second, that is exactly equivalent to value in charge in expressed in coulombs. So you now have some value that is expressed in coulombs. Since you also know the charge of an electron, which is 1.602 into 10 to the power minus 19 coulombs for one electron, you can just use this value to divide the value whatever you obtained here. So in order to find out how many number of electrons have been transferred in this reaction. Okay, so in this area. Okay, so from this you can find out the number of electron transferred if this reduction peak is because of a reaction which is involving only one electron transfer. Okay, for example, the reduction of nickel oxyhydroxide back to nickel hydroxide. This is a single electron reduction reaction, right? So in this case, you can directly assume that the number of electron, whatever you calculated from the charge you found out by integration and by normalizing it with the charge of the electron, you will directly take these electron values. I mean, the number of electrons, whatever you found out, can be considered equivalent to the number of nickel that is getting reduced from the form of nickel oxide hydroxide to nickel hydroxide. So this is how you can calculate the exact number of active site of an electrocatalyst. But again, if you have more than one metal, okay, and those metals are having inseparable redox behavior. For example, nickel and cobalt, and nickel and iron. And in those cases, it is always difficult to choose this metal. To choose this method, because in the presence of Fe, most of the nickel oxide hydroxide will be further oxidized to nickel 4. So there will be a separate redox couple between these two species, so which will not be accounted by the reduction peak. And we will always miss this proportion, this proportion of nickel, but we would be calculating something which is involving between these two couple. So when you have more than one metal and one metal is affecting the redox behavior of another metal, never use this method. So that is what I would say. But if you have some other metal which is not known to affect your another metal's redox behavior, for example, nickel and copper, they don't interact and they don't alter their redox characteristics. So in that case, you can integrate the area under the peak, and you can always assume that number of atoms you calculated is equal to the sum of the number of copper sites and number of nickel sites in the catalyst. But it is not applicable to all other system. It is applicable only to the system in which these two metals are not interacting in terms of their redox property in the chosen potential window. Okay, so this is how we can calculate the exact number of active sites from the redox peak. But you should also be very careful about the effect of scan rate, because when you increase the scan rate, there is always a chance that you will get lesser number for the number of active sites. ECAS value will be inversely related to the scan rate. So you should always also be careful about it, and you should always mention the scan rate from which you have calculated this value. So this is how you can do. I hope it looks so messy on the screen. I'm very sorry. So this is how you can do. Okay, so that is how you can basically calculate. Yeah, that's a you can calculate the number of active sites. Yes. Yeah, Mr. Dawal, I believe I have answered your question. Yeah. So yeah, Mr. Andrew, please, is it possible to give a demo how to run SCV in subsequent webinars? Yes, sure, Mr. Andrew. I'm actually planning on taking the session as slow as possible and as explicit as possible, because here we have researchers from every background. Those who have studied electrochemistry for years and years, like Subhash, and those who have just started, all of them are here. So I want to make everyone to be in line. So as we progress further, it will be useful, and it will be helpful to all present here. So if I directly right away jump to the SCV technique, some may not understand what is SCV, and some may understand, and some even find it be boring because they already know it. So I'll take it slowly. Yes, thank you, Mr. Andre. Yeah, so still we have got 7 minutes to go. If you have any doubts, yeah, Mr. Mundal, go.
Yeah, sure. So initially you have talked about two kind of adsorption, like specific adsorption and non-specific.
Yeah.
So is there any factor that will determine that what kind of adsorption will happen?
Actually, there is in Bokris and Reddy book, I remember I studied the ionic radii and electronegativity.
Okay.
Okay, electronegativity of anions and electropositivity of metals that is forming this respective metal cation can have some relationship to the specific adsorption or freely diffusing nature of the electroactive species. But this is in the case of some simple anions and cations. But for larger molecules, like people perform hydrogen peroxide sensor and glucose sensor, so many sensors are there. But in those cases, the species which is oxidizing or getting oxidized or reduced can always result in more than one type of product, and we don't know how the resulting product is interacting with the electrode surface, and how the unoxidized, the pristine active species, I mean the analyte, is interacting with the electrode surface. So there is always increased difficulty with the increasing size of the molecule and with the increasing probability of forming more than one product. So we should be mindful of all these things.
Okay.
Yeah.
Okay.
Yes, Dr. Dhanasekaran, please go. Dr. Dhanasekaran?
Yes. My last question is, for a turnover frequency calculation, I have used two metals, cobalt and iron. So for the turnover frequency, number of moles of active sites, which metal can I use? Which is actually taken for the active sites, considered as the active sites?
That is a question which has been under debate for more than 20 years now, and there is still a clear answer to that, because there has been so many advances in recent days. Some group claim Fe is the active site, some group claim cobalt is the active site, but nobody knows for sure. And but if you ask me, the number of people supporting the fact that Fe is the active site is higher in proportion when compared to the number of people, those who are supporting cobalt is the active site in the presence of Fe. But there are also people who says that both are active sites, but their intrinsic activity varies in the presence of one another. Okay, so this is a question which is being addressed for more than 20 years now. Have you seen the paper from Voyager Group published in Nature Catalysis 2 years back, in which they used isotopic labeling to find out which site is active site, Fe or cobalt?
Okay.
Yeah, in that paper you will find very interesting information, and I have discussed all these things. I mean, with the Fe containing electrocatalyst and the OER enhancing effect of Fe and the exact role of Fe in my recent review published in Nano Energy, and the title of the paper is the Fe effect. It starts like the Fe effect. Okay, in that paper I have discussed so much about the question whatever what you have asked. Okay, so you may go through that review. It is an open access review, you can download. And if you find it hard to understand, so I'll always be here next Saturday to help you out.
Yes. Thank you.
Yeah. And yes, Dr. Ravshek Rai, please.
Yeah, sir. Actually, I have one question that in acidic HER process, that in a Volmer step, the proton is stuck on the metal surface. In alkali, the water can do. But what is about in neutral?
No. Okay. Can you repeat the question?
Yeah, in a Volmer step, in a Volmer step, the proton is actually stuck on the metal surface when we do the HER reaction in acidic medium.
Yes.
Yeah, in alkali medium, the water can do this is same method. But what is actually occurring in the neutral medium when we take the buffer solution? Then what is actually occurring?
Yeah, in buffer solution, in neutral medium, there is a significant amount of proton, and mostly HCr occurs via the water dissociation coupled Walmer step. But unlike highly alkaline solution, there is also two mechanism. Actually, do you know the paper by Takanabe, Kazuhiro Takanabe, published in CatChem, I think, CatChem, 3 or 4 years back? He examined this behavior, particular behavior, how the reactant the selectivity towards the reactant varies in neutral medium when you have a buffer or when you don't have a buffer. So this he has done by taking cobalt electrocatalyst exclusively for HER and OER, and he found that at lower overpotential region, the HER happens always via the minimal proton, whatever is available in neutral medium. But when you increase the overpotential, the water dissociation coupled Walmer step is predominant. Okay, so just a moment. I may have the paper. I'll just a moment. Yeah. So I also discussed this thing in my review published in Advanced Energy Materials. You know, the paper title is Developments and Perspective in Water Splitting Electrocatalyst for Neutral and Near Neutral Water Electrolysis. Have you seen that paper? I have discussed this thing in that paper.
Okay, I will read, sir.
Yeah. So developments and perspective in 3D transition metals based electrocatalyst for neutral and near neutral water electrolysis. Okay, in Advanced Energy Materials 2020, page number is 1902666.
Okay.
Yeah, please read that paper and you can find that there. Yes, Subhash. Yeah, Mr. I, please complete.
Yeah, and this proton coupled electron transfer process, can we experimentally detect?
That's a tricky question. People have tried, including Nocera, but they cannot prove it experimentally. What they did is that they found some hypothesis and they proposed that cobalt is converting to cobalt 4 state and it is forming an oxane complex, cubane, cobalt cubane, in which there are 4 CO and 4 oxygen. This cubane is existing in some natural living beings where oxygen evolution reaction is done via this particular cubane, cobalt cubane like complexes, in which in the real case it is actually calcium and manganese, but the catalyst whatever the Nocera group used was cobalt phosphate. So they proposed a similar structure. To support this hypothesis, they have done ex situ EPR study. And there is a paper in JAX published 10-12 years before. What they have done is that they polarize the electrode at by setting a different anodic potential, and they froze the catalyst by immediately pouring liquid nitrogen, so that the oxidized cobalt stays in CO4 state for a while, so that they can place it in the EPR spectrophotometer and the signal of CO4 can be identified. And they proved that CO is getting oxidized to CO4 and it is forming a cubane like calcium manganese cubane like cobalt cubane structure. And this is what performing the oxygen evolution reaction exactly how the natural complex does with the proton coupled electron transfer path.
Okay.
Yeah. So if you have interest on this one, you can always read the papers by Nocera and his group. So they have done enormous work on that one.
Okay.
Yeah.
Thank you, sir.
Yeah. Subhash, please go.
I have one last question.
Yeah.
So whenever we are doing the LSV or CV, as I'm working on chlorine, I have to keep my reaction under continuous stirring. So there is a huge disturbance in my LSV or CV cycles. Instead of being linear, they will be like a sine wave. So is it okay that if we can apply a smooth function for
Does
that?
it look like a sine wave for real?
Yeah, it will look like a sine wave.
Sine wave means you see dipping trough below your x-axis.
No, I mean not in the electrochemically active region. I mean not in the Faraday region. Even in the Faraday region,
Okay.
let's say the current density is 50 milliampere, but they will look like a sine wave.
So what's the difference between the peak and trough in the current? What do you see?
Maybe 2 or 3 milliamperes.
Yeah, that is nothing. That is because of the disturbance that is occurring because of the convection.
Okay.
Yeah. You don't have to worry about that. If you are too worried about the convection, you can do one thing. Instead of stirring the solution, you can always use RDE. Because with RDE at high RPM, the laminar flow is quite uniform and you will not see such a disturbance.
Okay.
Yeah. Otherwise, if you want to perform these convection disturbance less accurate studies, always use ultra micro electrodes.
Okay.
Yeah. So may I know where you are working now, Subhash?
Now I am working in Hong Kong Polytechnic University.
Yeah. Okay, Subhash. Nice to know that. Yeah, you and your batchmates are in good places now. I'm very happy to see that. Yeah.
Sikri is a wonderful place.
Yes, Subhash. I cannot agree with you more. Yes. Okay. It's almost time. Yeah. Thank you all for joining today. Yes. Yeah, Dr. Dhanasekaran, I will share you and Parag Jawan, career opportunities. Yes. Yeah, someone is keep asking this thing. Okay, I'll definitely arrange a special session for discussing the things about career opportunities, in which I will invite a few of my colleagues, those who are working in Germany and UK. I am very sure they can be more of a source than me in this area, particularly the career opportunities side. So I'll definitely arrange a session such as that one. And until then, we'll continue to do what we are doing now. So please don't forget that if you want to participate in next week's discussion, you must register again, because as I have faced the spamming issue a couple of weeks before, I want to ensure that the same link is not used again and again, so that it can be used for spamming or some other unnecessary activity. So I will create a new link for every week's discussion, and you will have to register if you want to participate in the upcoming weeks. So please be reminded of that. And the meeting is currently being recorded, and once the recorded version is available, I will upload the video to my channel. You can always watch it later whenever you want to hear the decisions. Hear the answers, the clarifications I have given now on a later date. And thank you again for joining here. And Mr. Mondal, thank you very much. A big thank you to you. You have been of great help. And thank you all for joining today. Yeah, see you next week. Bye-bye, everyone.